Okay, so we are going to talk about discrete random variables, but the special ones. So I think I remember that I mentioned that now you know how to define the random variables mathematically, remember? However, you may kind of still feel like they are like some abstract being, like binatang apa sih itu? Because you don't have some concrete examples. So hopefully these special ones, they are really close to our daily lives, and probably you can visualize these events a little bit better. Okay. Yeah, you've seen this multiple times, but we'll go through this just one more time. You guys have already answered this on your weekly reflection, so hopefully everyone already has this definition down. So this random variable x is a function that assigns a number to any outcome of an experiment. We make an abstraction of each outcome and we just assign it to a number. Although this graph shows a one-to-one relation, but a random variable is not a one-to-one relation, so we can map more than one outcome to more than one outcomes to a single real value. We also learned that, okay, we transform our definition into a random variable, and we can compute the probabilities of those random variables based on these three distribution functions. So the probability of those random variables will follow some shape. Remember when we learned about distributions? It's going to follow that type of shape, that distribution. And we have three methods, or three functions that we can use to describe them: the PMF, the CDF, and the PDF. So the first one is, how can I compute the probability of the random variable being exactly that value, which is, what's the probability of my random variable being exactly that value? Or we can write it with a small p. The second one is the cumulative one. So when we're considering a certain value xi, we're no longer trying to compute the probability of that exactly, but anything less than and up to it. So we can also say this is the probability of x up until this certain value. We can also write it as fxi. And lastly, we can also consider a continuous one. Oops, my Zoom window is in the way. Give me a sec. The last one is the probability between two values, this probability here, which can also be written as the probability of my random variable being between a and b, which is the integral over ab of a certain function. So here, we already discussed this in class. It's the same if I use equals on the a part or the b part, that's the same. I can also do that. That will be the same, because the probability, if we're considering integrals, at one certain point is always equal to 0. So it doesn't matter if we use if we use the equals here or not. Careful for trick questions. If you are asked about to compute the top one and the bottom one, it's the exact same thing. So from these methods, the first two can be used to describe the discrete random variables, and the second two can be used to describe the continuous ones. We already learned that there are two different types of random variables, discrete and continuous. But there are some special discrete ones that you may recognize once we go through the definitions. So if you remember, last Monday, I asked each and every one of you, can you drive? I think I asked that question. And I'm going to just illustrate this point once again with another question. Okay, let's try. Let's try with who's the person on the top here. I have Amar here on the underneath my name. Amar, do you like K-pop? It's okay, no judgment here. No judgment zone. Amar, do you like K-pop? What?
No, miss, sorry.
No, okay, that's fine. Okay, let's try another person. Hello Moan. Hello Moan, do you like K-pop?
No, miss.
You do not. Okay. Let's try another person. Azra, do you like K-pop?
Biasa aja, Miss.
Okay. So you have to choose one. Remember, there's only a 1 and a 0. Make your mind up.
Well, I used to like, but right now, no, I think.
No? Okay. So I'm going to try one more. Fingers crossed. You guys can give me a hint in the chat box. Oh, Azra says yes. Okay, Dylan, you're going to throw Azra under the bus. What about I asked you? Do you like K-pop, Dylan?
The answer is obvious, miss. No.
No. Oh, too bad. Okay. Does anyone like K-pop in this class? Please tell me in the chat box, because my example is gonna get thrown out if nobody says yes. Dylan likes BTS. Is it because he really likes them or because they're trendy?
Not really.
Not really. Oh, okay. Let's go to Nafis. Nafis, do you like K-pop?
Of course, no, miss.
Really? I don't
Yeah.
believe you. Matthew
Why?
says. Matthew says you do. In the chat box, Matthew says. Oh, is it Matthew? Okay, let's go to Matthew then.
Yeah,
Matthew, do you like K-pop, Matthew?
I'm gonna say yes.
Thank you, the savior for today. So I can use this example. No, you can like K-pop too. So me personally, it's very catchy. I don't think I like it per se, but it is very, very catchy. Okay, so just now, every single question, every single person I called on could have given me a yes or no answer. You could have given me a 0 or 1 answer. And as such, I can have 2 possibilities. 1, if it's a success or you say, yes, you like K-pop, or 0 when you say no. So this is a failure, quote unquote, result. So there's only 2 different possible outcomes, yes or no, this or that, 1 or 0. So this is equivalent to the experiments that we have already seen in class, like the coin toss, head and tails, which we can assign 1 and 0 to. If we're talking about a valve, like a water valve, it's open or shut. An item, is it defective or not? So this is very often used, like if I buy a new laptop, will it be defective or not, for example? So this random variable where you have the probability of yes, there are only 2 values, right? There's only 1 and 0. So the probability of yes equals P. So obviously it's very easy to follow that the probability of x equals 0 will be 1 minus P. Why so? Recall when we were studying probabilities, the complements. So this is the case, because we only have 2 cases, right? Yes or no. And for that, we can also generalize the probability P, x equaling a certain value equals P to the power of x, 1 minus P to the power of 1 minus x, where this P, this probability is some number that we don't know, which is the probability that the trial is success. For example, in this class, what's the probability that a student likes K-pop? Probably quite low. Maybe in this case, from the small sample that we already took just now, maybe something like 0.05 or something. So that value would be this one, 0.05, for example. And thus the probability that X, a student likes K-pop equals 0 would be 0.95. Now, if we were to define that X is the probability a student likes K-pop, I can also write that as X follows, this is like follows the Bernoulli distribution with a probability of, in our case, in this class, 0.05. So if I were to talk about other events such as heads or tails, if it's a fair coin, then the probability, so let's say Y is coin toss, where 1 equals heads. So the probability of y equaling 1, if it's a fair coin, should be 0.5. And the probability of y equals 0 should also be 0.5. And as such, I can also write y follows the Bernoulli distribution with a probability of 0.5. Since we know these probabilities, oops, really sorry. So since we know these probabilities, so you may think that why do I need to know this probability? It's quite simple, right? It's the probability and its complement. Yes, you are correct. It's not really useful alone, but the Bernoulli random variables is a basis for many other distributions as well. So if we have the Bernoulli one, we can also then compute the expectation or mean, variance, and derive the CDF from the previously defined PMF. Okay, so just now, I repeated my Bernoulli exam, my Bernoulli trial, my Bernoulli experiment. Hey, do you like K-pop? I repeated it many times, right? I asked so many, I don't really remember how many people, but I asked many of you. So let's say I repeat it until I get to everyone in this class. This class, in my note, I have 19 of you in this class. So let's say I repeat this questioning to every single one of you in class. Do you like K-pop? Do you like K-pop? Every single person is being asked. So if I repeat that experiment 19 times, and I assume that each trial is independent from each other. So Dylan is not going to suddenly like K-pop if Nafis says he does, and vice versa. So if I assume that they're independent, and I already know that every single time I ask you, it's a Bernoulli trial, and it has a constant probability P of success, then if I do that, then I can also compute how many times do I get a yes in this class? How many times do I successfully get a 1 result, an x equals 1 result for every Bernoulli trial? So if in this class I did 19 Bernoulli experiments 19 times, each Bernoulli experiment, each time I'm asking you, we already considered a very low probability for this class, yeah? 0.05. So then if I now want to compute this one, the number of successes in my 19 trials, how many times do I get a yes from this class? So then I can say that this will follow a binomial random variable distribution with n trials and p probability. So in the case of this StatProb class, we would have y is the number of StatProb students who like K-pop. I can now write that y follows the binomial distribution of 19 students with a probability of 0.05 probability for every trial. Or in other words, it's the sum of n independent Bernoulli random variables. So if we have this definition, the binomial random variables, we can also compute the expectation, variance, and PMF from them. So PMF was not given here, yeah? So we have the PMF here. Okay. So when we now consider again the Bernoulli experiment, and previously we already considered, so one Bernoulli experiment can have either a yes or no answer. It could have a 0 or 1 or a success and failure. If I do it n times, I do it a fixed number of times, within that n, I can compute the number of times of getting a successful result. And that is the binomial random variable. And lastly, the third one is now when I have a Bernoulli trial, I have experiments that will give me either a 1 or 0, success, failure, yes or no. every single time when I ask you guys, do you like K-pop? You like K-pop, and so on. Each time I had a probability of success. And I had to try my question at least 7 times just now in order for me to get to Matthew that gave me a yes answer, right? So I had to do a number of trials until I get a yes, until I get a 1, until I get a success. And this number of trials can also be defined like here. If I have X trials, I want to know how many times do I have to actually do my experiment until I get a yes. So here, remember I have failures, right? I forgot who I asked, but I think I asked Nafis, I asked Halomoan, I asked Amar. Okay, failure. They do not like K-pop. And then voila, I get to Matthew and I get a yes answer. So at that X trial, I get a success. So if I compute those probabilities, I got a no, X minus 1 times. And I get 1x time on the X trial, I get a success. If I compute those probabilities, 1 minus P, 1 minus P for every single failure times P for that single success, that gives me the probability of X being X, in which my X in this case is the number of trials until success, then I can compute it based on that multiplication, 1 minus P to the power of X minus 1 times P. Just now, the probability of my X being a success, it took me 7 trials to get a yes from Matthew. And these types of random variables are also called geometric random variables. So when I have a series of Bernoulli trials, I know I need to do it how many times until I get a success. And such, I can also write it as X follows the probability of a geometric random variable with a probability of P. The P is still the same as our previously described binomial and Bernoulli random variables. It's a probability of success for every single trial. And based on this, we can also compute the mean, the variance, and the CDF that's derived from the PMF on the previous page. Once again, I'm going to ask your permission to skip over the examples. We'll do that on Monday. Okay, the first 3 random variables are based on the initial Bernoulli random variable. However, now let's consider we have objects, we have things to choose from. Like for example, I have n items. They are perfumes, for example. And among them, we have n special items, special edition ones, because if you buy that perfume, you get a bonus. Let's say, what is it, a certain coffee? You get a bonus lip gloss, for example. And if I go into this store that has 10 perfumes, among these 10, there are n perfumes, and among these there are special perfumes. Then if I choose at random any perfume in that store, any item in that store, the probability that I select a special kind is as follows. Makes sense, right? The number of special items divided by the number of total items. If I choose n items, a fixed number of items, small n, that is chosen with replacement. So if I choose one and it's special or not, and I put it back. So I keep working with the same number of items at every experiment. Then I can also say that this experiment, this random variable, follows the binomial distribution with the probability with n trials, so n times taking the perfume or taking the object, with every single time taking an object, we'll follow the R over N probability. Or if I did not put back the object, then I no longer have a binomial random variable. Remember, we already went through this in the quizzes. If I don't put back my perfume, if I don't put back my card, then I change the probability for every next trial, right? Because the first time I take it, whatever I take, I'm not giving back. So it's going to change the number of items that are in the store that are available for the next trial. And so that I can no longer use the binomial random variable, but I can use a hypergeometric random variable. In this case, we can say that X follows the distribution of a hypergeometric random variable with N. Here is the number of trials or the number of times I take the object, number of trials. R is the number of special objects, and N is the number of all objects. So here, this is the hypergeometric random variable, which can be computed based on that previous concept. We have our mean, our expectation, we have our variance, and we have our PM. I am going to go skip over the examples as well, just so we have enough time to cover the last random variable. So lastly, we have this final random variable that uses intervals as our boundary instead of the number of trials. So in our binomial one, I can compute the number of people who like K-pop based on the number of trials, how many times I'm asking. But now I have an interval. My limit is an interval. So for example, how many times does something occur within an interval? It doesn't have to be time, but I guess the easiest illustration would be time. For example, like the number of defects in an item, the number of defective items in a shipment, number of emails coming in an hour, a number of wrong calls, and so on. This is a Poisson random variable. It's not Poisson because it has double S, it's French, not Poisson, but this is a Poisson random variable. I can write an X as that follows the distribution of a Poisson random variable with the parameter alpha. So this is my rate. Alpha is my is the average number of events occurring in an interval of length t. So this is my rate. The rate, the speed of things happening, and the rate can also be computed by the average number of events of interval of each unit interval times the interval. So for example, if I know that I'm trying to compute the length, the number of emails occurring in a day, for example, in my whole day, and let's assume that my whole day is 24 hours, I know that I have 0.5 emails per hour. And as such, I can multiply that, and my alpha here would be 12. Be careful. Okay, based on the Poisson random variables, we can then compute variance, expectation, and the CPM. So what I would like to highlight here for the Poisson random variable is that you need to be careful that your units are consistent, because here we have per day, per hour, and so on, right? So sometimes your question will be asking hour, but you are given the information, the rates in minutes. You are asked about a whole working day, which is 8 hours, for example, but you are given the rate in hours. So be careful with your units. That is the trickiest part, I believe, in solving a question regarding the Poisson random variable. So I know that my time is up, but I'm going to ask your permission to give you one example of Poisson before we close the class. So here we have the arrival of a customer in the store that has a Poisson distribution of 5 visitors per hour. So let's see. Here we have 5 visitors per hour. Let's compute the probability that there are less than 5 visitors. This is very bad English, I'm sorry. The probability that there is less than 5 visitors in 1 hour. So we're going to compute the first one. So let's know what information we have. We have our rate 5 visitors per hour. We now have our time or our duration, our interval, which is in 1 hour. So 1 hour. And now I want to compute that the probability of, I'll put X is the random variable that describes the number of visitors in 1 hour. So I can write that that X follows the Poisson distribution of lambda times T. And in this case, it is 5 times 1. It just so happens it's the same thing. It's P. And I can plug it into the equation that I know. This is using the CDF. We are given the CDF here. And now we can compute the probability of X being less than 5. Note here that 5 is not included because it says less than 5. And for the next one, the probability that the number of visitors equals 10, exactly 10. So remember, when we're computing the probability of an exact number, we can use the PMF. And note, in a day. So now our T is 24 hours. So here we have the information in rates of an hour, so 5 visitors per hour, but you are asked to compute in a day. So you sometimes need to do some conversions between units of measure and ensure that you have the correct unit in place before you compute your alpha, because that will affect your computation of Poisson.